Hello everybody, I hope you're doing well and that you're safe. I am making this video because I had to do a recording for my biology class and I am quite nervous that my audio submission didn't go through on Canvas, so I thought it'd be a good idea to post it on YouTube. And since it's been a while since I posted because this class has taken up much of my time as well as the other two, I thought it would be fair if I drew a little something to go along with it. So I drew red blood cell because today I'm going to be talking about the bicarbonate buffer that is found within your blood cells. So hopefully this was all correct and you guys don't bully me too hard for stumbling over my words because biology is not easy. And I hope you're able to enjoy the drawing and have a great day. Alright, so this recording is going to be to explain the two pictures given in this class. It is explaining how the bicarbonate buffer affects the blood cells both in the alveolus and when it is just delivering oxygen to tissue cells. So because the tissue cell picture is at the top, I will begin there. In this picture, the red blood cell is delivering oxygen to tissue cells and receiving the carbon dioxide from those tissue cells. We'll start with the tissue cells giving carbon dioxide because that's kind of like the main way this entire formula starts. Carbon dioxide enters the red blood cell and it fuses, or bonds, with the water ion, which can be found inside the red blood cell. This is because of carbonic anhydrase, which is an enzyme that causes this reaction to occur. Once the two form together, they're principles. They're ions, essentially, as carbon dioxide is a single carbon with two oxygens, and water is two hydrogens and one oxygen. They fuse together and create carbonic acid, which is two hydrogens, one carbon, and three oxygens. Now, in this blood cell, this carbonic acid, it is a weak acid, but it is there to be adjusted to ensure that the pH level inside the blood is neutral and remains neutral. So in this blood cell, because of the carbonic acid, even though it is weak, it is making the pH level a little bit closer to, it's leaving the 7.35 range. And so because of this, it gets rid of its positive hydrogen and then becomes bicarbonate, which is a single hydrogen, a single carbon, and three oxygens. And it is negative because it lost its positive hydrogen. Now, this bicarbonate will exit the red blood cell, and because, as mentioned before, we want to keep the blood as neutral as possible, losing a negative means that another negative needs to re-enter. The negative of choice is chlorine, which then enters the blood to make sure that balance is maintained. Now, the hydrogen that was expelled needs to bond with something, and so it remains in sort of red blood cell limbo until you have the carbaminohemoglobin. This is towards the bottom of the red blood cell. So what happens is that carbon dioxide enters and bonds with the hemoglobin, which then creates hemoglobin carbon dioxide, which is HbCO2. Now, underneath that, you have HbO2, which I don't know if that derives from the HbCO2. The carbon in that just said, "You won't catch me in these streets." She just disappeared. But underneath that, you have the hemoglobin and oxygen. And so what happens is that the hemoglobin will attach itself from the oxygen and will then instead fuse with the hydrogen, which can be noted in the farthest right side of this picture, as you see HHB, which is the hydrogen and hemoglobin together. And then all you have left is the oxygen, which is then expelled and given to the tissue cells, which was the red blood cell's purpose all along, because all your tissues need oxygen. But now that the red blood cell no longer has its oxygen, it will now return through the cardiovascular system to get to the alveoli for gas exchange to become reoxygenated. So when this happens, the blood travels down to the capillaries, which is then closest to the alveoli, and can now receive oxygen. So it expels the CO2 it has gathered from the tissue cells in the original picture, and instead it takes in the O2. The O2 will then bond with the hydrogen hemoglobin that we saw earlier, and that turns it into hemoglobin O2 plus a positive hydrogen. Now, when this happens, the bicarbonate that exited originally and went to the blood plasma will re-enter the blood cell. And because you can't have too many negatives, this triggers the negative chlorine to leave the blood cell, as it is no longer needed since there is a negative within the blood cell again. This bicarbonate will then fuse with the positive hydrogen that was given up from the oxygen hemoglobin chain before, and because it has rejoined the bicarbonate, it returns to becoming a carbonic acid. Now, when this happens, this triggers the carbonic anhydrous. I swear I know how to say these when I'm not recording. This triggers that enzyme to cause them to separate once more, which then pulls that bond apart and creates carbon dioxide and water once more. Now this has happened, the red blood cell can expel the carbon dioxide as needed and give it to the alveoli, which then send it through the bronchioles and the lungs. And after this, it can be expelled through your nose or your mouth, or however you're expelling your carbon dioxide. Those are the primary, I guess, sort of like chains throughout the blood cell, but I will make note of the other parts of the picture. The thickness of the arrows represents how much is being taken and given throughout the cell. For example, in the picture showing the red blood cell giving oxygen to the tissue cells and receiving carbon dioxide in return, as you may notice, the thickest arrow is the oxygen leaving the blood cell, and there's a very small pink arrow representing the oxygen being taken through plasma, as oxygen can't enter the plasma proteins. However, majority of your oxygen will come from your red blood cells. Similarly, majority of your carbon dioxide comes from the interstitial fluid as opposed to directly from the cells themselves. A little bit does come from tissue cells, but majority of it comes from that interstitial fluid, which separates the two. Similarly, underneath that, when we look at the alveolus alveolus graphic, you see that majority of the oxygen comes directly from the alveolus, and majority of the carbon dioxide comes from the red blood cell. However, some of it does come from the plasma, and some of it is thinner than others. Another thing you may have noticed is that some of the chains have fast or slow on them. For example, we're looking at carbonic anhydrous. There, I said it. I said it properly for once. Looking at that enzyme, you'll notice that it says fast because this is the fastest reaction within the blood cell, whereas the other fusions or separations of ions is a little bit slower. Similarly, when you look within the plasma, those sort of groupings or formulas are a lot slower than they would be within the blood cell, because quite frankly, plasma is important, but when it comes to the blood cell, that's where all the good stuff is. So that has to be taken care of a little bit more. But besides that, that is what the graph represents, and that is why the bicarbonate buffer is so important, because we need it to function and make sure our red blood cells can operate properly. Well, thank you for making it this far. Consider this an audio test for those of you who do not care about my biology life. I understand if you don't. Please let me know in the comments if this sounded good, or if my voice, if there's anything I need to do to make myself sound more clear. But until then, stay safe, everybody. Take care.